Hello and welcome to MacMod Analytical's hosted webinar, New LC Particle Technology, Monodisperse Fully Porous Particles. This will be the first of 3 chromatography in 20-minute webinars. My name is Alex Nase and I will be filling in as moderator for Ed Faden, who unfortunately couldn't be here today. For those of you who are unfamiliar with MacMod, we are a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the most innovative columns and accessories to our customers. We also provide application notes, technical reports, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. Today, we will be discussing UHPLC and HPLC columns that are packed with monodisperse, fully porous particles, the advantage of this new particle technology, and how to leverage the increased efficiency to improve the resolution of your complex separations. If you have any questions during this presentation, please type them into the chat window and include your name and company. We will do our best to answer as many questions in the allotted time slot as possible. We will send out a follow-up email to everyone after the webinar with the slides and a link to a recording of the webinar. Today's talk will be given by Geoff Faden. Geoff Faden is the president and CEO of MacMod Analytical. He received his Bachelor of Science in Chemistry from Penn State University in 2003 and his MBA from Temple University in 2014. He has served as a trusted chromatography partner for the life science industry for over 15 years. He has experience working with major pharmaceutical, biopharmaceutical, industrial chemical, and environmental companies to improve their analytical workflows and provide innovative solutions to their challenging chromatography-related problems. He has been acknowledged in several publications and posters and has frequently been counted on to provide industry-leading technical support, presentations at conferences, meetings, and on-site lunch and learns at customer facilities. Thank you for joining us today, Geoff.
Thank you, Alex. Really excited to be here. Thanks for all that are online on the webinar. Today's talk will be New LC Particle Technology, Monodisperse Fully Porous Particles. Okay. So when we talk about monodisperse fully porous particles, you sort of want to go into, well, the history of how HPLC particles were designed. And it's a fairly long history. The technologies really came about in the mid-50s. You had the morphology of the particles, which talk about how the particles were shaped. You have irregular, you had now spherical. You had also the size of the particles. Over time, we've had the size really reduced from early 100 micron down to now even 1.3 micron particle sizes. Over time, you've had purity as a measurement, how pure the silica is or other material that you're using is, what the metals content is. And so over time, you had type A and then now type B silicas, which are less metals content. And then the innovation we're talking about today is around the distribution of the particle size. And so that's what we're going to get into. So with these monodisperse fully porous particles, what I'm showing here on the slide is a Coulter counter. And what you see is when most commercial manufacturers talk about their silicas or their HPLC columns on the market, they're talking about the mean particle size as the particle size you see on the box, which would be, let's say, 5 micron or 3 micron. Here we're showing 2 commercially available, fully porous 3 micron materials. The way you look at particle size distribution is, let's take the count of particles at the 90th percentile and divide them by the count of particles at the 10th percentile. The closer those two numbers together get to 1, the more monodispersed the material is. And as you can see here, the Evosphere material that we're talking about today has a very tight band as compared to the Gaussian bands of the commercially available silicas. So what we show is in column A here, where the monodisperse silica, the mean particle size is approximately 2.66, although it depends on what technique you're using to measure that. And then you have commercial silicas that we showed on the previous slide at 2.48 and 2.97. You can use other means like the scanning electron microscope and things. But what the key point is that the D90/10, the way we measure whether or not it's monodisperse, is this value D90/10. So that way you can see visually, and also you can see here in the table, you're looking at a 40% reduction in D90/10, where the monodisperse silica is at 1.12, and the commercial silicas are much closer to 1.6. And what that looks like visually here on the left, you can see the polydisperse material is what we're calling the standard commercially available silica, and now the new monodisperse material using a scanning electron microscope. So this equation, you've seen this, I'm sure, from many other vendors. It's the resolution equation. There's many articles about this equation, but the one point I want to talk about first is the efficiency. So the resolution equation is measured by three factors. You have the efficiency term, the retention, and the selectivity. The way you measure efficiency of a packed column is you take the length of that column and you divide it by the height equivalent to a theoretical plate. So the question becomes, well, I know what the length of my column is, but what's the height equivalent to a theoretical plate? Well, one way to look at it is what we call the simplified Van Deemter equation. You've seen this everywhere, and you have H, which is equal to the height equivalent to a theoretical plate, are based on three terms. You have the A term, the B term, and the C term. The A term is your Eddy diffusion, which is your multipath effect. The B term is this longitudinal diffusion or molecular diffusion as the band crosses the column. And the C term is the resistance to mass transfer. It's how the mobile phase goes in and out of the stationary phase. But what you need to sort of think about, and when people show these, they don't really break it down into the actual components of the Van Deemter equation. So what we did here was try to focus on, okay, well, of these each terms, how do I understand this? It's nice, okay, A, B, C, great. But what if I was to actually look at the math behind it? So let's start with the C term. The R value, D squared F, that's for gases. So that goes to 0 in liquid chromatography. The B term in liquids, the B term, the diffusion of liquids isn't very wide, so the B term tends to go to 0. So you're really left with the A term and the C term. For small molecules, the C term happens so fast that it's basically minimized. And so at that point, you're really looking even simplified even further to this A term. What you have there is 2 lambda dp. And so dp is the particle size diameter. And then you have lambda, which is this packing factor. And that's what is really being compressed when you talk about monodisperse material. You're really minimizing that packing factor so that you can minimize the height equivalent to a theoretical plate, which means I can fit more of those plates into a column. So what does that look like visually? Well, on the top, you can see what we would call our evosphere monodisperse material, and then sort of a graphical representation or a pictorial representation of what a non-monodisperse or polydisperse material looks like. And you can see as analytes travel through the column, naturally, if they don't have a lot of interstitial space to go through, you're not going to get a lot of band dispersion going down the length of the column. So what does that mean? Well, you get tighter peaks. So what does that look like chromatographically? Almost a 60% increase in plates. Well, so you're like, okay, well, I have a material that gives me 60% increase in plates. That's interesting for the particle size. That sort of sounds like superficially porous or core shell material. So what's so cool about that? Why is this interesting? Well, when you compare core shell to evosphere, what you have here is 3 times the surface area on a fully porous material. And so what that means is you're going to get similar efficiency, but you're also going to get greater loading capacity because you're going to have more time for the analyte to interact, which means I can inject more on the material. The materials act the same, slightly less efficiency at low flow rates, but at higher linear velocities, similar efficiency. And so here's just another example of how it improves loading and increases retention. Again, more area means more retention, which means I get more K. And as I load onto the column, I'm not losing efficiency. So I can have 1 meg, 2 megs, 3 megs per mil, and I'm still maintaining the efficiency on the left trace with Evosphere, but on the right trace in the core shell, you start to see it overload at about 2 megs per mil for a well-acting analyte. And I think the important thing here is say, okay, well, great. So I have a really efficient material. I'm going to have it based on the back pressures. I'm going to have similar benefits to what the core shell material is, but I'm going to have more retention and I'm going to have more loading capacity. Okay, well, that's cool. So what do I do with that? So I have my resolution equation. I go back to my terms and say, okay, well, I have efficiency. I've optimized that. Now what I'm going to look at? Well, I'm going to look at selectivity because selectivity we know is the key to resolution. It has the greatest impact. It's almost linear to resolution. So how do I leverage selectivity? Well, I bond different selectivities, different bonded phases that bring different modes of interaction to the party. So here are the 8 commercially available small molecule bonded phases that I can talk about. So here we have Evosphere, C12, that's interesting. It's not a C18. Everybody says, well, why don't you have a C18? It's like, well, why do you need another C18? You know, is the response we tend to give. It's like, okay, if C12, actually, I can bond more C12s onto the silica surface and give you a more hydrophobic environment. It gives you more hydrophobicity, a little bit less steric selectivity, but you have some polarity. This is my favorite phase, I say. It's the diphenyl, and it's a diphenyl hexyl, which is interesting because with phenols, they tend to bleed at low pH. And so if you could stabilize the phenyl character on the silica, you get more phenyl character and less bleed. And it gives you an interesting selectivity for different analyte sets. You have the C18PFP. This is for regioisomers. This is my go-to chemistry. You have C18AR, also excellent, very interesting data we'll show in webinar 3 on oligonucleotides with the C18AR. For the aqua, this is in polar end capping, and that gives you more retention for some moderately polar compounds, while named aqua because it can use 100% aqueous mobile phases. RP18 amide for some of these new structural nitrosamines and also for bases, a low pH. An RPM, it is absolutely a tool you should have in your toolbox. It gives you a different mode of interaction. You have a phenylhexyl, which is a 6-carbon chain, so that brings something different, and then also a short chain phenylfluorophenyl. Again, regioisomer selectivity there with the short chain, a lot of ion exchange capacity, and also has that U-shaped retention curve for Hillock operation. So the key point when I went back to the loading capacity is like, okay, well, that's cool. I can then maybe scale a prep. I can keep my particle size changing and change methods, translate methods from maybe AR&D to a receiving lab in another country and make sure I get the same selectivity. So that's one of the things that is available in this fully porous material, that you can retention time stay consistent even though the particle size is changing, but you can also obviously with the particle size reducing increase your efficiency. Like pharma, I mean, everybody in pharma is going to want to know that batch-to-batch reproducibility, multiple batches are available. You can't have a product unless you have batch-to-batch stability. Here's what the columns look like, and then the new box. So definitely something to keep your eye out for. We did here's sort of an intro using the technology. We did a project with Dr. Tim Garrett at the University of Florida, who runs the Metabolomics Center. We're going to show just some interesting mass spec data. What we used was the C18PFP because for metabolomics, you have a lot of small molecules that are difficult to retain and can be very similar. Here's the conditions, and the total ion chromatogram was a 2.1 by 100, 3 micron column. We used a Q exactive and then just a simple mobile phase of 0.1% formic acid and water and acetonitrile. And the power of this new material is really exciting. So these compounds, 5-aminopentanoic acid and valine, the log P of these are -2, 2.3, and you're retaining them in reverse phase. That's interesting. I mean, that is a real powerful tool that if you have polar analytes and you can retain these in reverse phase reproducibly, that it doesn't, you don't have to go to Hillick, you know, you don't have to use ion pair, you don't have to try to run it at high pH. It's an interesting benefit, which I was talking about before. I mean, this tends to be a crowd pleaser. You have isoleucine and leucine here, and if you see there at about 3.3, you're starting to see allo-isoleucine break out on this 3 micron. We are showing later on the metabolomics work that we do with the 1.7, that actually starts to pop out even further. But small positional changes, the regioisomer selectivity really is powerful. Acetylcarnitine, you have that charged amine there, quaternary amine. That's going to give terrible peak shape on a C18, but you have really nice low metals content, monodisperse, high efficient silica. You're getting beautiful peak shape. Strong isomeric selectivity with tyrosine and phenylalanine is a nice one. And then the lysophospholipid isomers of SN1 and SN2. You can see that here you're able to separate these things. One very close molecular structure, but slightly differences. That's how powerful the phase is, and using it on the monodisperse particles. So we wanted to, because this is a chromatography in 20 minutes, we wanted to just talk about, there are some further line extensions. The materials available on a 300 angstrom pour now, the C12, diphenyl, C4, and C18AR are all available on 300 angstrom materials. We're super excited about this technology as applied to oligonucleotide therapeutics, and we're going to show something really special in part 3 with a collaboration with a university in Poland. And here, this is a 100 angstrom material, C12 and C18AR, but it's using a coated hardware, which is necessary for the really sticky acidic oligos. And then we also now offer for some of your other more pesky peptides and proteins, we offer the 300 angstrom in what we call our Biomax hardware, the chemically inert hardware. So with that being said, in conclusion, I was able to do that in 20 minutes, so I get a gold star. Monodisperse fully porous particle technology eliminates the weaknesses and combines the strengths in traditional superficially porous and fully porous particles, giving you the best of both worlds. This new technology offers efficiencies similar to superficially porous particles without loading limitations and the ability to scale to preparative sizes, which provide significant method development advantages. Thank you, and stay tuned for part 2 and part 3.
Thank you, Geoff, for that wonderful presentation. We have a few minutes to answer questions from the audience. I want to remind everyone that you can type any questions into the chat window. Please include your name and company. That way, if we do not get to all the questions, we can follow up with you after the webinar. So, first question, Geoff, how easy is it for me to translate an older method to a monodisperse particle method?
Well, how easy is it? I guess it depends. The type A silicas can be have a high ion exchange character. So what we would want to say is you want to start from sort of first principles and do method scouting. We would want you to look at scouting gradients. If you wanted to actually just drop one column in for something else, it's a little bit like playing Russian roulette. It may or may not work, but we can certainly help you redevelop your method, and would love to get the opportunity to do that.
Okay. Another question. How are the pH and temperature limitations for these particles compared to other fully porous and superficially porous particles?
So it's silica. The significant innovation here is how the silica is being made and controlled to deliver the monodispersity. So silica in general has pH limitations above pH 8, and as you go to higher temperature, so you want to be careful there. The C12 can use um, uh, we've seen it stand up in ammonium hydroxide, and for 10,000 column volumes, which is pretty impressive. And we think that's due to the significant coverage of the ligands because it's optimized with carbon C12 versus C18. You don't get any of the steric hindrance, which means you have to use less end capping. So what I would say is, as you increase temperature, you increase the mechanism kinetics, but I would also say it stands up very comparably to the industry standard, materials.
Okay, unfortunately, that's all the time we have for today. If you did ask a question that we did not get to, we will follow up with you via email. On behalf of MacMod Analytical, I want to thank Geoff for a terrific webinar and remind you that we have 2 more webinars in this chromatography in 20-minute series. UHPLC monodisperse particle column technology and its applied use in metabolomics and lipidomics studies, which will be held April 16th at 1 p.m. Eastern, and UHPLC monodisperse particle column technology and its applied use in oligonucleotide separations without ion pairing additives, which will be held on May 14th at 1 p.m. Eastern. Be on the lookout for emails to register for those soon. Thank you for attending the first webinar of our chromatography in 20-minute series, and we hope to see you at the next one on April 16th.